I'm going to jump the gun a little bit and go to the t distribution, because I mentioned the t distribution. The normal distribution in a population, they talk about the z-scores of 1.96 or 2.58 indicate the limits on either side of the mean, at which 95 and 99% of all the observations fall. Okay. Normally, we don't know the real values of a population. We don't know the real values of the population. And we use our sample means to estimate these. Okay, and because the samples are large, we assume that our estimates are reliable. When the samples get smaller, we are not as sure that we are including that large percentage or 95% of the population. So what happens is, to compensate for this, those values of 1.96 or 2.58 are increased, okay? And we call that the t-value, and the t-value is based on the number of samples where I can assume that 95% of the population lies. Okay, so in other words, that t-value becomes a function then of the standard deviation. Okay. And we normally look that up in a t-table. So in other words, if I have a large population, okay, 95% of the population, I use the value of 1.96. And you saw how I got that. But as the population gets smaller, or as the number of samples, gets smaller, I'm not so sure where 95% of my population lies. And I have to use a bigger value, or the t-value becomes bigger. Okay, so in other words, 95% of the population, if I only do 10 measurements, I have to use 2.2 times the standard deviation to be certain that I've got 95% of my population. If I have a very large number of samples, I use the value of 1.96 times the standard deviation, and I can be sure that I've got 95% of my population in that. Okay. So these are not numbers that are drawn out of a hat. They are related to the behavior of the population, or that certain characteristic within the population. Okay. Now, why do I want to know all that? Okay. I've tried to keep it simple. So I hope you're still on my wavelength here, because this can become very complex. Why do I want to know that? Because I want to compare populations. I want to know if one population differs from another. And if I don't have a measure of the variation in the two populations, I can't be sure that they're overlapping or they're actually separate. Okay? And this is where the t-value becomes very important in working out whether the populations overlap or they don't overlap. Okay? So when I have two populations, or if I do some measurements, I can work out the deviation from the mean.
Excuse me. You have pointer, please use pointer.
I hate the pointer, but I'll do so. Okay, so here you can work out your t-value. You look at your deviations from the mean divided by the standard deviation, okay, and it gives you a value. So if I have two values, I have a standard deviation, I can work out a t-value, and if the t-value is bigger than whatever it's telling me in the table, I can tell you the populations are the same or the populations are different. So let's take an example. I have a sample of 12 seeds. I work out the mean diameter of the seeds, and the seed diameter is 5.43 millimeters, and the standard deviation of those 12 seeds is 0.62 millimeter. Already I can tell you now about the population of seeds, right? It has a mean of 5.4, and its standard deviation of 0.62. Okay. I now found a seed that's lying around in the laboratory. Dropped that. Who was it who mentioned the seed that got thrown out in the Petri dish earlier? Okay. Was that actually just part of the population, or was it actually better, or was it worse? Okay. Was that my magic seed? Right. I measure the diameter of that seed. It's 0.44 millimeters. Okay. It's less than that number. The question is it likely that this comes from a population with the same mean from which these 12 samples were drawn? Okay. Right. I then take the mean, which is 5.43, and I subtract that from 4.4. Okay. And I divide it by the standard deviation. So I have 4.4 minus 5. Okay, so it's basically 1 millimeter difference. Divided by the standard deviation, I get a value of 1.66. Now don't look at the sign. It doesn't matter if it's positive or negative. Okay. 1.66, I have 12 seeds. I have 11 degrees of freedom. Remember the degrees of freedom? I had a table somewhere. 12 seeds. Okay, this table is only going to show 10, but let's work on that. So the value is 2.2. In my calculation, I've got 1.6. Okay, the calculated t-value is less than that. The seed can be considered to have come from that original population. I cannot say with certainty it's different. Okay, so you see where the t-value starts becoming useful, where the mean is useful, where the standard deviation is useful. Okay. If I calculated, and I've got that on my spreadsheet, I won't go into it now, but it's there for you to calculate. If the difference there was more than 1, let's say it was 2, and that value was then double the, so it was what, 3.2. It's bigger than the table t-value. In other words, I can say that the seed comes from a different population. It's not part of that population. So that's in a simple form, the way in which the t-value, the standard deviation, the mean, and everything else comes together.
So do you have to clarify that with a statement with 1 chance in 20 of making a type 1 error?
I'll get to type 1 and type 2 errors when we get to ANOVAs. Let's. I think I'm confusing them enough now.
Okay.
Okay, right. So although it looks complex and all the rest, it's actually very simple. Okay, because I have a mean, I have a standard deviation. I can express the standard deviation as a percentage. Gives me a picture. I can use the standard deviation to then work out where 95% of the population lies, and I can then start looking at, do things deviate from our population or not? So in other words, if the calculated t-value is then greater than whatever the table value is, depending on the degrees of freedom I have, I can say populations are the same or the populations differ. Okay. So that is essentially, maybe that's a reasonable stopping point at this time. But only quickly, remember that we were basing this on a normal distribution. Very often, when we go and collect data, data can be skewed. So the population can be biased towards one side or biased towards the other. So there I have a normal population. You can see the mean, and I'm more or less evenly distributed on either side of the mean. Very often we end up with data like this. And it becomes important that we look at the distribution of our samples because most of our statistical programs assume that data is normal, and most of your statistical programs have a mathematical test for normality, and I'll bring that up tomorrow. Okay. I just want to make a point that there are a lot of transformations that can be used if data is skew to make it normal, so that we can make the correct assumptions about what is going on in the population. And I'll come back to that as well. Just as an example here is a figure. You can see the distribution is skew. All I did was applied a log transformation and you got a better distribution of the data. Okay, so there are ways that if your data is not normal, you can normalize it in the sense of, or using transformations. Okay, so, and there's a whole lot I've got there. And I think maybe that would be a reasonable place to stop. That you understand the concept of measurement, randomness, bias, distributions, means, standard deviation and variance, okay, and the t-test, and what the meaning of t is. Okay, right, questions? You are welcome.